Hello. So in this video, it's sort of a follow-up to our logarithmic differentiation. So when we sort of developed logarithmic differentiation as a tool, we saw how powerful it could be, right? It took something that would have been just awful to try to take a derivative of and made it, at least the derivative process, pretty sort of straightforward and nice. But at the time, we also sort of made a note that this is a very specific use case, right? There's a very sort of tight area where we can actually use this thing. So it's sort of a natural follow-up and really an important question to ask: when can we use it? How do we recognize sort of the situations where we want to use logarithmic differentiation as opposed to sort of tackling something that might just be hard, right? That is always a possibility. So that's our goal for this video. We want to determine when is this technique useful, or when can it be used, and sort of red flags that tell us when it decidedly should not be used, when this would be a bad idea, okay? So remember, when we used it, logarithmic differentiations, the primary strength came from leveraging those rules of logarithms, right? Using those logarithmic rules to sort of rip apart that really tightly sort of compact factored form that we were dealing with. So the general rule of thumb is that that's what you use it for. Logarithmic differentiation should only be used when your function is in a form that allows you to use your rules of logarithms to break it up. So I realize it's sort of a very mathy answer, so we're going to go through a couple examples to sort of see what we mean by that. So let's say we have this kind of thing. Now, you could tackle this with a triple product rule, and it wouldn't be awful, but it wouldn't be fun. But you could also do this with logarithmic differentiation, right? If you applied natural log to both sides, you could then use your log rules, because they're all being multiplied together, to break them up, right? So then this triple product becomes a triple sum, and sums are nice for taking derivatives. So this would be a decent use case. This would be a situation where it would be pretty reasonable to use logarithmic differentiation. But what happens if we take the same thing, but add a -7, right? So notably, this is no longer a fully factored expression, right? I have a bunch of factored stuff, -7. So now, if I apply my log rules, well, I have natural log of y equals natural log of stuff -7. But remember, my natural log could only break stuff that's being multiplied together. So now that I have that -7, I am sad, right? There's nothing I can do with it. I can't break this apart with log rules. So applying logs to both sides has really just made it legitimately even harder, right? It just added extra steps to what was already going to be a difficult process. I should not use logarithmic differentiation here, okay? So another example, even if I only have two sort of factors, if I have higher powers, right, fourth power and second power, this is another situation where logarithmic differentiation can make some sense because, again, everything is being multiplied, right? It's fully factored, and those higher power pieces can come out as these coefficients using log rules. So this lets me break it up relatively nicely. But again, sort of going through all of these things, if I have a situation where, here I have, for example, multiply and divide, but it's still fully factored, right? So again, if I can look at this and say it's fully factored, and so that means that I can use my log rules, I can break it up, and so this works, right? So here, because all of these things are sort of factored completely, top and bottom, I can break it up by using all of those log rules. But as soon as I introduce something that isn't factored, right, the top here, right, the bottom is fully factored, the top not fully factored. So now if I apply my log rules, I can only get so far because I can pull out this bottom part, right, because I have all of the top times the bottom to the -2, or divided by the bottom to the square power. So I can break up that piece, for example, but the top, because it's not fully factored, there's nothing I can do with that. So Here we get into a little bit of a gray area because it depends on sort of how factored one part is versus the other part. Is it easier to take the hit and make one of them harder, in this case the top harder, in order to make the other one, in this case the bottom, easier? In this case it's not, because the bottom is not that bad, but if the bottom were a really, 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 really long piece with a bunch of products in it, maybe it would be worth sort of taking the hit, making the top part harder to deal with a little to be able to break apart the bottom fully, right? So it can get into a gray area depending on exactly the situation, but the rule of thumb is that if you have pieces that aren't factored, those pieces, right, if it's the top or the bottom in a fraction, or if it's the whole expression, that piece is not going to be something you can really get anywhere with logarithmic differentiation, okay? So what did we do? We talked about logarithmic differentiation. It's a very powerful tool, right? We've seen it used in a way that sort of saved us a lot of time with the derivative, but really it's only for fully and completely factored functions. That's really its wheelhouse, where it's really good to be used. If there's any extra terms, right, if we have anything that isn't fully factored, even some +1 at the end of some long factored thing, everything falls apart because we can't use log rules on any of it as soon as we have that single little bit of like +1 or -7 at the end, right? So if there's any of that, everything falls apart. And the only way you can really sort of try to salvage it would be to multiply everything out so that you could then factor everything if it's even factorable. That's a whole rabbit hole you don't want to run down. So most all of the time, you're just going to want to sort of go ahead and tackle it directly with a lot of product rules or whatever you need to do at that point. Okay? So that's that.